In this lecture, we will see the characteristics of the equilibrium constant. So, what are the characteristics in which the equilibrium constant depends? Number one, it does not depend on the initial mass or concentration or pressure of the reactant. So, this is the important point. It never depends on the initial mass or concentration or pressure of the reactant or product. It has a definite value. The equilibrium constant has a definite value for every reaction. So every reaction has a one definite value of this reactant at particular temperature. So for a one temperature, the K has a one particle value. If you change the temperature, then the value of the K will also changes. Number second, the numerical value of the equilibrium constant indicates the extent of the reaction can proceed. Like this, if the value of K is greater than 1, then the equilibrium will lies to the right side, means equilibrium moving to the forward direction, that is production of product is favored. If the value of K is lesser, very less than 1, then the equilibrium will be towards the left side. This means that the equilibrium is proceeding towards the backward direction, that is the formation of the reactant is favored. Now in case of third, so K for the backward reaction is the reciprocal of the K for the forward reaction. So K for the backward reaction is reciprocal of K for forward reaction. So let us see from these examples. Suppose this is the hypothetical example. A2 plus B2 is undergoing reversible reaction 2AB. So Kc will be equal to, so concentration of AB by using the law of chemical equilibrium. So concentration of AB whole square divided by A2 concentration of A2 by concentration of B2. Now just reverse this equation, 2AB reversible to A2 and B2. So write the new Kc for this reaction. So again if you see this reaction, so this reaction nothing but the again one new Kc. So Kc is equal to 1 by Kc. So this is nothing but the reverse of Kc. So Kc for the backward reaction nothing but the reciprocal of Kc for forward reactions. Similarly, we can take the case of this one, N2 plus 3H2 is equal to 2NH3. This is the K1. So again, if you take the reverse process, then we have to write the 1 by K1. So this is also one of the important mathematical approach for the equilibrium constant for forward and backward reaction of equilibrium constant. Now in case of next one, Kc is independent of the presence or absence of any inert substance. So if the any inert substance is present or it is absent, like catalyst also, including catalyst also, so Kc do not depend. So it is not depend like the initial mass or concentration, does not depend on the catalyst or any inert substance. So catalyst simply, what is the use of catalyst? It simply helping attaining equilibrium earlier. So it does not vary with time. So inert substances should not react with reactant or product. So this is the important point, that the inert substances is not depending on the K, but it should not react with a reactant or product. Then it is independent of any inert substance, that is K. Fifth point, the equilibrium constant, it varies only with the temperature of the reaction. So it depends on the temperature of the reactions and constant only at a given temperature. For one particular temperature it is constant, but if you change the temperature, the K will also changes. So both Kp and Kc are independent of the pressure of the system. So N2O4, this example of N2O4, it is undergoing dissociation of two molecules of NO2. So we can see at 298 Kelvin this is the 0.98, and at 400 this is the 47.9. But if you increase the temperature, it becomes 1700. So Kp is increasing. Similarly, in case of formation of ammonia, you can see at 298 Kelvin, this is the value of Kp. But if you increase the temperature, again it is decreasing. For again, if you increase the temperature, it is decreasing. So it depends. So if you increasing temperature, the Kp may decrease or increase. It depends upon the type of equilibrium. So next point is, it is independent of the direction from which equilibrium has been attained. So it is also not dependent on the direction. It can be come from the forward direction. Equilibrium can be achieved from the backward direction. So any direction you can achieve it. Equilibrium constant changes if coefficient of various species in the equation are multiplied by some numbers. So like this example, H2 plus I2 is 2Hi. So here equilibrium constant for this reaction is something 49 at 711 Kelvin. Now multiply this whole equation by half. So if you multiply whole equation by half, it becomes half Hi plus half I2. So here we are multiplying. So after multiplying, this becomes your Hi. So equilibrium constant will be your, this is Hi and this is the square root of H2, this is square root of I2. So here K2, this is nothing but the square root of K1, that is equal to 7. K1 is here 49, so square root of 41 is 7 at 711 Kelvin. So So we can write K2 is equal to nothing but the square root of K1. So if you multiply by half, it becomes a square root. If you multiply a square, it becomes a square. So like this it is varying. So when the equation for the equilibrium is multiplied by a factor, K must be raised to the power equal to the factor. So this point is very important. So K must to the raised to the power equal to the factor. Next point, when addition of two equilibria leads to another equilibrium, then the product of their equilibrium constant gives the equilibrium constant of the resultant equilibrium. So how? Let us see these examples. So here I am taking three equilibrium. So one is nitrogen plus oxygen. It will give you two molecules of nitrogen oxide. So that is oxide. This is nitric oxide. So here equilibrium K1 is the equilibrium constant for this reaction. Similarly, another equations 2NO plus O2, 2NO2. So at the same temperature, the equilibrium constant for this reaction is K2. Now you take the third equation, N2 plus 2O2. So here equilibrium constant is 2NO2. So this is nothing but the addition of this 1 and 2. So now add the first and second, it will give you third. So this is the addition of first and second. So this is cancelling this this way and this one. So N2 plus 2O2 give you 2NO2. So but this is K3. So K3 is nothing. So if you multiply K1 into K2, so this is the K1, this is the K2. So on multiplying you will get this value. Now this value is nothing but the K3. So if you take the more, yes, that is the, if the more, that is the sum of the two equilibria is always multiplication of 2. Like if you multiply 3, 4 equilibria, that is also equal to the sum total of the fourth equilibria or fifth equilibria. So like this is the another numerical value which is useful in calculating the problems. Now if equilibrium constant is expressed in terms of concentration, so it has different unit for different reactions. Like Kc is written as a mole per liter, but if you take in terms of Kp, so we write atmosphere, or it depends on the stoichiometry of the equations. So let us see for Kc. Suppose in a particular reaction, moles of the reactant is equal to moles of the product. Like this is equation. So here H2 plus I2. So here 2 moles of Hi, and in reactant side is 2 moles of Hi. So Kc becomes unitless. Similarly, in case of N2 plus O2, 2NO2, so here 2 moles, here also 2 moles. So again, Kc or Kp both become unitless. Kc is also unitless and Kp is also unitless in these cases. But if you take the number of moles of reactant different from that of product, that is PCl5 is converted into PCl3 plus PCl2. So here Kc is this much. So write the concentration mole per liter, this will cancel. So here Kc has some value. So value of unit is mole per liter. Similarly, in case of ammonia, write the Kc first and write the whole unit. So you will get here per mole square per unit square. So this is the unit for this reaction. So in generally term we can write Kc is equal to concentration to raise to the power delta n. So delta n is the nothing but the moles of the product minus the moles of the reactant. Use this value. If it is negative, it can be positive or it can be 0. So delta 1 is nothing but the moles of the product minus moles of the reactant. Similarly, we can use for the Kp for this reaction. So similarly, Kp for this reaction has the unit atmosphere per atmosphere square or per bar square. So the unit of Kp is nothing but the unit of pressure raised to the power delta n. So this is atmosphere raised to the power delta n or bar raised to the power delta n. What is delta n? Delta n is nothing but the number of gaseous moles of the product minus number of gaseous moles of reactant. So in this way we can find the unit for Kp or Kc, or by identifying the unit we can find what is Kp, what is Kc. Both can be possible.